The Voyager mission stands as one of the most remarkable and enduring achievements in the history of space exploration. Initially conceived as a brief mission to explore the outer planets of our solar system, Voyager has far exceeded its original objectives, transforming into a journey that has provided humanity with an unprecedented understanding of the cosmos. This unexpected voyage, now lasting over 4 decades, continues to send valuable data back to Earth, hinting at an unexpected discovery that could defy all our current understanding of physics.
NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again, after months of spouting gibberish.
Join us as we dig deep into Voyager's terrifying discovery after 46 years in space. The story of Voyager began in the early 1970s when NASA recognized a rare celestial alignment that would allow a spacecraft to visit all 4 of the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, in a single mission. This alignment, occurring once every 176 years, provided an opportunity to use the gravitational pull of each planet to slingshot the spacecraft to the next, reducing the time and energy required to explore these distant worlds. NASA's Jet Propulsion Laboratory, also known as JPL, designed 2 spacecraft, Voyager 1 and Voyager 2, to take advantage of this unique alignment. These spacecraft were equipped with a suite of scientific instruments designed to study the atmospheres, moons, and magnetic fields of the outer planets. Launched just weeks apart, Voyager 2 on August 20, 1977, and Voyager 1 on September 5, 1977, the twin spacecraft embarked on their respective journeys, each following a carefully plotted course. Voyager 1, the faster of the 2, was initially aimed at Jupiter and Saturn. In March 1979, Voyager 1 made its closest approach to Jupiter, capturing stunning images of the planet's turbulent atmosphere, its great red spot, and its many moons, including the volcanic Io and the icy Europa. The spacecraft's observations revolutionized our understanding of these celestial bodies, revealing active volcanoes on Io and the possibility of a subsurface ocean on Europa. After its successful encounter with Jupiter, Voyager 1 continued to Saturn, arriving in November 1980. Here, it provided the first detailed images of the planet's intricate ring system and discovered the haze-shrouded moon, Titan. Titan's dense atmosphere, primarily composed of nitrogen and methane, intrigued scientists as it hinted at the complex chemistry that might resemble early Earth. However, due to its trajectory, Voyager 1's encounter with Titan sent it on a course out of the plane of the solar system, ending its planetary tour but marking the beginning of its journey into interstellar space. Voyager 2, following its sibling's path, reached Jupiter in July 1979 and Saturn in August 1981. Unlike Voyager 1, Voyager 2 was programmed to continue its journey to Uranus and Neptune. In January 1986, Voyager 2 became the first spacecraft to fly by Uranus, providing humanity with its first close-up images of the planet and its moons. It discovered 10 new moons, 2 new rings, and noted the peculiar sideways rotation of Uranus. In August 1989, Voyager 2 reached Neptune, its final planetary target. It provided stunning images of the planet's deep blue atmosphere, characterized by supersonic winds and large storm systems, including the Great Dark Spot. Voyager 2 also flew by Neptune's largest moon, Triton, revealing geysers of nitrogen gas and surface features indicative of cryovolcanism. After their encounters with the outer planets, both Voyager spacecraft were redirected towards interstellar space. In 1990, NASA announced the beginning of the Voyager interstellar mission, a new phase focusing on the outermost edges of the Sun's influence and beyond. Despite their advanced age and the vast distances involved, the spacecraft continued to operate, transmitting data from the farthest reaches of the solar system. One of the most iconic moments of the Voyager mission occurred on February 14, 1990, when Voyager 1, at the request of astronomer Carl Sagan, turned its camera back towards Earth and took the famous pale blue dot photograph. From a distance of about 3.7 billion miles, Earth appeared as a tiny, fragile speck in the vastness of space. This image, along with Sagan's reflections on it, has since become a symbol of humanity's place in the universe and our responsibility to cherish and protect our home planet. On August 25, 2012, Voyager 1 made history again by becoming the first human-made object to enter interstellar space, crossing the heliopause, the boundary where the sun's solar wind is overtaken by the interstellar medium. This milestone marked humanity's first foray into the space between the stars, providing a direct measurement of the conditions in this uncharted region. Voyager 2 followed, entering interstellar space on November 5, 2018. The data sent back by both spacecraft have been invaluable, offering new insights into the density, temperature, and magnetic fields of the interstellar medium. These findings challenge existing models of the solar system's boundary and deepen our understanding of how stars, including our Sun, interact with their galactic environment. But to gain a deeper understanding of the breathtaking discoveries from Voyager, it is important to first consider the environment in which the Voyager spacecraft are traveling. Interstellar space is the region beyond the influence of the Sun's solar wind, where the spacecraft have now ventured. This space is not empty. It contains a sparse distribution of gas, dust, and cosmic rays, as well as magnetic fields that permeate the galaxy. However, this region is vastly different from the space within our solar system, where the Sun's influence dominates. One of the key differences between the heliosphere, the bubble of space dominated by the Sun's influence, and interstellar space is the nature of the plasma that exists in these regions. Inside the heliosphere, the plasma is hot and diffuse, primarily composed of particles emitted by the Sun. In interstellar space, the plasma is cooler and denser, originating from ancient supernovae and other stellar processes. And one of the most significant discoveries made by the Voyager spacecraft in interstellar space is the detection of a new kind of plasma, or ionized gas, that exists in this region. Unlike the plasma found within the heliosphere, which is dominated by the solar wind, the plasma in interstellar space is much denser and cooler. This discovery was made possible by Voyager 1's plasma wave subsystem, which detected the oscillations in the plasma caused by the spacecraft's movement through interstellar space. The detection of interstellar plasma has provided scientists with valuable insights into the nature of the interstellar medium. For example, the density of the plasma suggests that interstellar space is not as empty as previously thought. Instead, it is filled with a diffuse but measurable amount of matter that permeates the galaxy. This finding has important implications for our understanding of the processes that govern the formation and evolution of stars and planetary systems. Another significant discovery made by the Voyager spacecraft in interstellar space is the observation of cosmic rays, high-energy particles that originate outside our solar system. The spacecraft have detected a dramatic increase in the intensity of cosmic rays since crossing the heliopause, indicating that the heliosphere acts as a shield, protecting the inner solar system from these energetic particles. The study of cosmic rays is crucial for understanding the radiation environment in space, which has implications for the safety of future human space exploration missions. The Voyager spacecraft have also provided valuable data on the magnetic field in interstellar space. Unlike the Sun's magnetic field, which is structured and relatively strong, the magnetic field in interstellar space is much weaker and more chaotic. This has led scientists to reconsider their models of how magnetic fields interact with the interstellar medium and how they influence the movement of cosmic rays and other particles through space. Interestingly, beyond the known phenomena of magnetic fields and plasma waves, There is a realm of speculation that considers the possibility of the Voyager spacecraft encountering more exotic forms of matter or energy. One of the most intriguing possibilities is the concept of dark matter and dark energy, which are believed to make up the majority of the universe's mass and energy, yet remain largely mysterious. Dark matter is thought to interact with regular matter primarily through gravity, and it is distributed throughout the galaxy in a vast, diffuse halo. While dark matter does not emit light or other electromagnetic radiation, it could exert a gravitational force on the Voyager spacecraft, potentially altering their trajectory in subtle ways. Detecting such an effect would be extremely challenging, as it would require precise measurements of the spacecraft's motion over long periods of time. However, if such an interaction were detected, it would provide a groundbreaking new piece of evidence in the study of dark matter. On the other hand, dark energy is a force that is believed to be driving the accelerated expansion of the universe. It is even more mysterious than dark matter, and its effects are thought to be only noticeable on the largest cosmic scales. However, some speculative theories suggest that dark energy could have more localized effects under certain conditions. If the Voyager spacecraft were to encounter a region of space where dark energy behaves in an unexpected way, it could produce forces that are currently beyond our understanding. Another speculative idea involves the concept of exotic matter, which includes hypothetical particles and fields that do not conform to the known laws of physics. Examples of exotic matter include tachyons, particles that travel faster than light, and negative mass, matter that would exert a repulsive gravitational force. While there is no direct evidence for the existence of exotic matter, the possibility that it could exist in some form in the universe remains open. If the Voyager spacecraft were to encounter such matter, it could produce forces that would be entirely unexpected and potentially revolutionary for our understanding of physics. Also here, while speculative, another possibility that captures the imagination is the idea that the Voyager spacecraft could encounter evidence of extraterrestrial technology. Given the vast distances involved, the likelihood of such an encounter is extremely low, but the concept raises fascinating questions about the nature of intelligence in the universe and the potential for contact with other civilizations. If the Voyager spacecraft were to encounter an artificial object or a signal from an extraterrestrial civilization, it could be interpreted as an unknown force affecting the spacecraft. This could manifest as an unexpected change in the spacecraft's trajectory, unexplained signals or interference in its communications, or even a direct response to the Golden Record, an artifact carried by both Voyagers containing information about Earth and humanity. The discovery of extraterrestrial technology would have profound implications for our understanding of the universe and our place within it. It would suggest that we are not alone and that other civilizations have achieved the capability of interstellar communication or travel. This possibility, while speculative, continues to inspire both scientific inquiry and public imagination. That's why NASA always tries its best to keep its aging heroes alive. The agency has kept the Voyager spacecraft service for more than 4 decades through a combination of innovative engineering, resourceful power management, and skilled mission oversight. Launched in 1977, Voyager 1 and Voyager 2 were initially expected to operate for about 5 years to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune. However, their mission has extended far beyond this, with both spacecraft continuing to send data from interstellar space, well beyond the influence of the Sun. A key factor in the longevity of the Voyager spacecraft is their power source, radioisotope thermoelectric generators, or RTGs for short. These RTGs convert heat from the radioactive decay of plutonium-238 into electricity, providing a steady power supply. However, as the plutonium decays over time, the power output gradually decreases. To manage this dwindling power, NASA has carefully prioritized which systems and instruments to keep active, systematically shutting down non-essential components to conserve energy. For instance, the spacecraft's cameras were turned off in the early 1990s, and heaters for some instruments have been reduced or turned off entirely to save power for more critical systems. Communication with the Voyagers, now billions of miles away from Earth, is another challenge that NASA has successfully managed. The Deep Space Network, or DSN, a global system of large radio antennas, is used to maintain contact with the spacecraft. As the distance between Earth and the Voyagers has increased, the signals they send back have become extremely weak, often just a fraction of a billionth of a watt. To ensure continued communication, NASA has upgraded the DSN's antennas and employed advanced data compression and error correction techniques, allowing the spacecraft to send back valuable scientific data despite the immense distance. Navigating and orienting the Voyagers in space requires precise control of their gyroscopes and thrusters, which are used to adjust their position and direction. These systems also consume power, so NASA has reduced their usage by placing the spacecraft in a low-power mode and minimizing the frequency of maneuvers. The spacecraft rely on their last known orientation, with occasional adjustments to ensure they remain properly aligned for communication and data collection. The scientific instruments on board the Voyagers continue to provide groundbreaking data about interstellar space. NASA has prioritized the instruments that offer the most valuable information, such as the Plasma Science Experiment, Cosmic Ray Subsystem, and Magnetometer, while turning off others that are less critical. The data collected is processed and compressed by the spacecraft's computers before being transmitted back to Earth at a slow but steady rate. Throughout the mission, NASA's team at the Jet Propulsion Laboratory has played a crucial role in keeping the Voyagers operational. By continuously monitoring the spacecraft's health, updating software, and developing creative solutions to technical challenges, the team has been able to extend the mission far beyond its original expectations. As the Voyagers venture further into interstellar space, NASA's careful stewardship ensures that these remarkable spacecraft continue to push the boundaries of human knowledge. And now, as of 2024, both Voyager spacecraft continue to transmit data back to Earth, despite being more than 14 billion miles away from the Sun. But as the saying, "all good things must come to an end," Voyagers are approaching the limits of their operational life. The power available to the spacecraft is gradually decreasing, and it is expected that by the mid-2020s, the spacecraft will no longer be able to operate their scientific instruments. When this occurs, the Voyager mission will officially end, but the spacecraft will continue their journey through interstellar space, potentially for billions of years. Even after the Voyager spacecraft cease to function, their legacy will endure. The data they have provided has revolutionized our understanding of the outer solar system and interstellar space, and their journey represents a triumph of human ingenuity and curiosity. The Voyager spacecraft also carry with them the Golden Record, a message intended for any intelligent extraterrestrial life that might encounter the spacecraft in the distant future. The record contains sounds and images that represent the diversity of life and culture on Earth, serving as a time capsule of humanity's existence. While the Voyager spacecraft will eventually be too distant to communicate with, and the Golden Record may face degradation over time, the record stands as a testament to human ingenuity and the quest for knowledge. Its creation and launch were driven by the desire to send a message across the cosmos, and its ongoing journey is a reminder of both our place in the universe and our enduring quest to understand it. The Voyager mission's exploration of interstellar space has profound implications for our understanding of the universe and our place within it. Moreover, the Voyager mission has inspired a new generation of scientists and engineers to explore the frontiers of space. Having said that, the success of these missions laid the foundation for a new era of planetary exploration. The technological and scientific advancements demonstrated by Voyager had a lasting impact on the design and objectives of future missions. One of the most direct continuations of Voyager's legacy is the Galileo spacecraft, which was launched in 1989 to explore Jupiter and its moons. Galileo, equipped with instruments and technology inspired by the Voyager missions, provided detailed observations of Jupiter's atmosphere, its complex ring system, and its major moons, including Io, Europa, Ganymede, and Callisto. The data collected by Galileo built upon the discoveries made by Voyager and offered new insights into the dynamic processes occurring on these moons, particularly the volcanic activity on Io and the subsurface ocean beneath Europa's icy crust. Another mission directly inspired by the Voyager missions was the Cassini-Huygens mission, which launched in 1997 to study Saturn and its moons. Cassini, a collaboration between NASA, the European Space Agency, and the Italian Space Agency, was equipped with advanced instruments to investigate Saturn's rings, atmosphere, and magnetosphere, as well as its diverse moons. Cassini's detailed observations of Saturn, including the discovery of water ice plumes erupting from the moon Enceladus and the identification of a thick atmosphere on Titan, built upon and expanded the knowledge gained from Voyager's flybys. The Huygens probe, which descended through Titan's atmosphere in 2005, provided the first direct analysis of this moon's surface and atmospheric composition, further enriching our understanding of Saturn's complex system. The Voyager missions also inspired missions to other parts of the solar system and beyond. The New Horizons mission, launched in 2006, was designed to explore Pluto and the Kuiper Belt. New Horizons made its historic flyby of Pluto in 2015, returning detailed images and data that revealed the dwarf planet's diverse surface features, including vast plains of frozen nitrogen and towering mountains of water ice. The success of New Horizons can be traced back to the pioneering spirit of the Voyager missions, which demonstrated the feasibility of long-duration missions to distant worlds. In addition to planetary exploration, the Voyager mission's achievements influenced the development of missions aimed at studying the heliosphere and interstellar space. The Voyager spacecraft, having crossed the boundary of the heliosphere, have provided invaluable data about the nature of interstellar space. This data has informed the design and objectives of missions like the Interstellar Probe, a proposed mission to explore the outer reaches of the heliosphere and beyond. The Interstellar Probe aims to build on the legacy of Voyager by reaching even further into the interstellar medium and investigating the interaction between the solar wind and the interstellar environment. The Voyager mission's impact extends beyond direct scientific successors. They have inspired new approaches to space exploration and mission design. The concept of sending spacecraft on long-duration journeys to explore distant regions of space has become a guiding principle for many subsequent missions. The development of advanced propulsion systems, deep space communication technologies, and autonomous operations has been driven by the need to emulate and build upon the successes of Voyager. For example, the James Webb Space Telescope, launched in 2021, represents the culmination of decades of technological advancement and is designed to observe the universe in infrared wavelengths, providing insights into the formation of stars, galaxies, and planetary systems. The cultural and philosophical impact of the Voyager missions cannot be overstated. As told, the golden records carried by the spacecraft, intended as a message to potential extraterrestrial civilizations, symbolize humanity's desire to communicate and connect with the broader cosmos. The records, which contain greetings in multiple languages, music from various cultures, and images of life on Earth, reflect a universal hope to reach out beyond our planet. This message of unity and exploration has inspired public interest and support for space missions, contributing to the continued funding and development of ambitious projects. The Voyager missions also serve as a testament to the spirit of international collaboration in space exploration. The data and discoveries made by Voyager have been shared with scientists worldwide, fostering a global effort to understand our solar system and beyond. This collaborative approach has been instrumental in advancing our knowledge and in promoting a sense of unity in the pursuit of scientific and exploratory goals. In summary, the Voyager missions have left an indelible mark on space exploration, inspiring a wide range of subsequent missions and technological advancements. Their legacy is evident in the continued exploration of the outer planets, the study of the heliosphere and interstellar space, and the development of new space missions and technologies. The impact of Voyager extends beyond the scientific realm, influencing cultural and philosophical perspectives and fostering international collaboration. As the Voyager spacecraft continue their journey into the vast expanse of interstellar space, their influence remains a testament to human ingenuity, curiosity, and the unyielding quest to explore the unknown. While awaiting incredible new discoveries from the Voyager twins from the immense darkness of interstellar space, billions of miles from Earth, let's take a quick look closer to our home. NASA's Chandra X-ray Space Telescope has created a three-dimensional map of stars close to the Sun that may help astronomers search for alien planets that could host life. The map created by Chandra, which just celebrated 25 years in orbit but is facing a troubling budget crunch, could inform scientists which exoplanets to direct future telescopes toward to conduct searches for habitable conditions. The stars mapped by the telescope are arranged in concentric rings around the Sun, at distances between 16.3 light-years and 49 light-years. This is close enough that telescopes could collect wavelengths of light or spectra from planets in the habitable zones of these stars. The habitable zone, or Goldilocks zone, is a region around a star that is neither too hot nor too cold to allow liquid water to exist on a world's surface. The spectra from these planets, created as starlight shines through their air, could potentially reveal surface features like continents and oceans, and atmospheric characteristics like clouds and chemical contents. Chandra's X-ray capability is key to selecting which planets to investigate for possible habitability. High-energy light like X-rays and ultraviolet radiation can strip a planet's atmosphere and also break down the complex molecules needed as the building blocks of living things, ruining its habitability. Thus, if Chandra sees a planet under heavy X-ray bombardment, scientists can infer it isn't the best world to study in the search for alien life. As Brianna Binder of California State Polytechnic University, the leader of the team behind the new map, said in a statement, "Without characterizing X-rays from its host star, we would be missing a key element on whether a planet is truly habitable or not. We need to look at what kind of X-ray doses these planets are receiving." Binder and colleagues built their map by initially starting with a list of 57 stars close enough to our solar system that future telescopes in space, like the Habitable Worlds Observatory, and on terra firma, like the Extremely Large Telescope, could image planets orbiting in their Goldilocks zones. Just being in the habitable zone isn't a guarantee that a planet is hospitable, however. Venus and Mars are both in the habitable zone of the Sun on either side of Earth, but the Martian surface seems to be unsuitable for life as we know it, and superheated Venus is outright hostile to it. So, to narrow down their list, the team used data from 10 days of Chandra observations and 26 observing days of the European Space Agency's XMM Newton Space Telescope to see how bright the stars are in X-rays. Then, they determined how energetic these X-rays are and how rapidly the star's X-ray emission changes. The scientists reasoned that the brighter and more energetic the X-rays were, the more likely any orbiting exoplanets had sustained serious damage to their atmospheres or lost them entirely. As team member Sarah Peacock from the University of Maryland explained, "We have identified stars where the habitable zone's X-ray radiation environment is similar to or even milder than the one in which Earth evolved. Such conditions may play a key role in sustaining a rich atmosphere like the one found on Earth." Some of the stars examined by the team are already known to be orbited by exoplanets with masses and sizes similar to the solar system giants Jupiter, Saturn, Neptune, and Uranus, with a handful of candidates under around half the mass of Earth. There could also be planets in these systems with masses and sizes more compatible with Earth's that are currently undiscovered. Earth-sized planets in these systems may have been missed by the most reliable method of exoplanet detection, the transit method. This technique depends on a planet crossing or transiting the face of its star, causing a tiny dip in the output of starlight in the process. This depends on a planet coming between its star and Earth, meaning some systems just aren't oriented correctly to see worlds with the transit method. The technique is better at spotting massive planets close to their star, so smaller worlds that orbit relatively far away could be missed. The other primary exoplanet detection technique, the radial velocity method, hinges on spotting the wobble a planet causes as it orbits its star and gravitationally tugs on it. Again, this method favors massive planets close to their stars, which generate a more significant wobble. As team member and University of California, Riverside researcher Edward Schwieterman concluded, "We don't know how many planets similar to Earth will be discovered in images with the next generation of telescopes, but we do know that observing time on them will be precious and extremely difficult to obtain. These X-ray data are helping to refine and prioritize the list of targets, and may allow the first image of a planet similar to Earth to be obtained more quickly." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.